All right, class, we're going to pick it up where we left off, talking about colligative properties. Remember, colligative properties really rely on the identity of the solvent that's involved. So when we look at these examples, really doesn't come down to much other than that. They rely on the identity of the solvent involved. So there are two of them that you're responsible for. Freezing point depression. Remember, we talked about that. Seeing that effect when we put ice out on our, or not ice, but salt, lay salt out on the ice in the winter. What happens is the salt dissolves in the ice and lowers the freezing point of the water, therefore making the ice melt most of the time. And then the boiling point elevation, we talked about why we add salt to a pot of water that we want to boil. What happens is the salt causes the boiling point to be elevated, so when we actually put our pasta in or whatever, it's going to cook quicker because that water is at a higher temperature. Excuse me, but beyond that, we do have two ways of mathematically computing both the freezing point depression. As you can see here, we have a triangle TF. That triangle is change in. It's the Greek letter delta. It means change in temperature. The F represents freezing, so what that says is a change in the freezing point temperature is a function of the freezing point constant, which will be provided for you, but it's negative 1.86 times the molality of the solution. And the boiling point elevation can be calculated very similarly. In this case, it's change in temperature boiling, okay, TB, equals, again, the boiling point constant, which is 0.51 degrees Celsius per molal, which will be provided for you, times the molality of the solution. So those are the two formulas to compute these. So let's look at a problem. We did this one in class, but I'll review it now. To help here, it says, what is the freezing point depression of water in a solution of 17.1 grams of sucrose, C12H22O11, and 200 grams of water? What is the actual freezing point of the solution? Well, there's three steps to solving this problem. The first step, we've got to convert from grams of the sucrose given, 17.1 grams, to the number of moles contained in that mass, using the molar mass of sucrose, which we can compute using the periodic table. So we see that we have 12 moles of carbon, each weighing 12, 22 moles of hydrogen equal each weighing 1, and 11 moles of oxygen, each weighing it at 16. Yeah, multiply all that together, add it all up, you get 342.34. So when we divide 17.1 grams by the 342.34, you come out with 0.05 moles of the C12H22O11. Our second step is, now that we know the number of moles of sucrose, we can then figure out the molality by using the molality formula, which is molality equals number of moles of solute, in this case sucrose, divided by the kilogram of solution. So this problem gave us 200 grams, okay, of the solvent. Excuse me, I meant to say solvent. Okay, you divide moles of solute by kilogram of solvent. In this case, we're given, as you can see here, 200 grams, okay, of our solvent. So we've got to convert that. I did not show that, but 200 grams is equivalent to 0.2 kilograms. And when I divide the number of moles of the sucrose, 0.05, that we computed in step 1, by 0.2 kilograms, we get 0.25 molal solution of sucrose in water, okay? So we have a 0.25 molal solution, again, of sucrose in water. So our third step then is to actually use the new formula to figure out the actual freezing point depression, which is change in temperature of freezing equals the freezing point constant times the molality of the solution. So when we put in are given, which will be provided for you on test, but the freezing point constant is negative 1.86, and multiply that by the molality we computed in step 2, we come away with a change in temperature of 0.465 degrees Celsius. So you notice in the math over here, I showed you that when you do the math out, molality gets canceled out, and we're left in a numerator with degrees Celsius, which is what we want. So that's actually the change in temperature. So what is the actual end temperature the question is asking for? Well, we know that ice melts freezes at 0 degrees Celsius. So adding a little sugar will depress that freezing point by negative 4.65 degrees Celsius, and 0 degrees plus negative 0.465 is going to get us a resultant freezing temperature, perceived freezing point temperature of negative 0.465 degrees Celsius. Okay, the second problem we didn't get to really in class, but it's similar. This time it says a water solution containing an unknown quantity of a non-electrolyte solute is found to have a freezing point of negative 0.23 degrees Celsius. What is the molal concentration of the solution? Now, I told you from the beginning of the year, 90% of the formulas that you have to work with in chemistry are 3 variable equations, and that's true of the freezing point depression formula. It's got 3 variables. So what we want to do first is take that formula, okay, changing TF equals the KF times the molality of the solution, and then write out our given information. In this case, we're told the actual change in the freezing point temperature. It changes by negative 0.23 degrees Celsius, and we're given, and we will be given on test, the freezing point constant of negative 1.86 degrees Celsius per molal. Okay, so we're given those 2 things. Now we're looking, as I square it off here, the problem's asking us to figure out what the molality of the solution is. Well, we've got 2 of the 3 variables, so now it's just a matter of plugging it in and applying some 8th grade algebra to this thing. So when we do so, we get negative 0.23 degrees Celsius is we plug in for the change in TF here, okay, and then we add in our negative equals negative 1.86, which is our change, or KF, our freezing point constant, times our molality. Doing a little algebra, we divide both sides by negative 1.86 degrees Celsius per molal to leave molality by itself. When I do so, I come up with a molality of 0.12 mole. That's my solution's molality, and that's the answer to the question. Okay? All right, let's do a few problems that actually involve boiling point elevation. What is the boiling point elevation of a solution made from 20.1 grams of a non-electrolyte solid? Notice they keep stressing non-electrolyte. That's important. We'll get to that in a second. But we have 20.1 grams of a non-electrolyte solute and 400 grams of water. Now, the molar mass of the solute is 62 grams. Listen, if they're not, like this problem, if it doesn't give you the actual identity of the non-electrolyte solute, it has to give you its molar mass so you can compute the number of moles contained in our given 20.1 grams. And that actually, ladies and gentlemen, is our first step. Step number 1 is to use the molar mass of this unidentified non-electrolyte solute, okay, to figure out the number of moles contained in 20.1 grams. And we do that by setting up the unit analysis problem so that grams gets canceled out. And we're left with moles, okay? We've been doing that almost from day 1 in this class. We must be masters at this point. So we figured out 0.324 moles of solute. Now I know the number of moles, and I also know the amount in grams, but I still know the mass of the solute, which happens to be water again. So I can use step 2, the molality formula, okay, which is the molality equals the number of moles divided by the mass in kilograms of the solvent. I plug in my 0.324, which was calculated in step 1, moles, divided by, again, 400 grams converts into 0.4 kilograms. I don't show that, I just did it, but there's your explanation. So 0.324 moles divided by 0.4 is going to get us 0.81 molal solution. So our molality is 0.810 molal. Now we know the molality, and we're provided the boiling point constant. So step 3 is just simply solving the algebraic equation for the change in the boiling point elevation. Okay, so change in TB equals the boiling point constant times the molality of the solution that we calculated in step 2. Over here, this will be provided for you, but the boiling point constant is 0.51 degrees Celsius per molal. And again, when I do this math, my unit for molality cancels out. I'm left in with the numerator with my unit for degrees Celsius. So this non-electrolyte added to this water solvent is going to raise the boiling point temperature by just shy of half a degree, 0.41 degrees Celsius. All right, this is why last time I stressed, okay, the fact that the last few problems have dealt with non-electrolyte solutions. Let's talk about an electrolyte solution. Okay, there is a significant difference between the two. This problem says, what is the expected change in freezing point of of water in solution of 62.5 grams of barium nitrate? Barium nitrate is a salt. If I add it, the barium and the nitrate, the ionic bond will dissociate, okay, and I'm going to get barium plus 2 ions, cations, dissolved in water, and the nitrate minus 2 ions dissolved in water, okay, or minus 1 ions dissolved in water. So the first thing, because we've got to first calculate the molalities to figure out the number of moles contained in my given 62.5 grams. When I do that using the periodic table, I figure out that the molar mass of barium nitrate is 261.35. Notice that grams gets canceled out. I'm left with moles. So I have 0.239 moles contained in 62.5 grams of the barium nitrate. Okay, step 2 is a little bit different. Step 2, you actually have to write out the formula for the dissociation of this salt in water. And the reason why you have to do that is I'm starting, okay? I'm taking this guy and I'm putting him here. Okay? That's how many moles of my initial salt I have. Okay? When I dissolve this in water, I produce 1 mole of the barium plus 2 and 2 moles of the NO3 minus, for a total of 3 moles. So, because this is a 1 to 1 to 2, okay, if 0.239 moles of the initial salt is going to produce 0.239 moles of the barium plus 2, and then 0.239 times 2, or 0.478 moles of the nitrate. And when I add all that together, I get 0.717 moles, overall moles of ions between the 0.239 moles of the barium plus 2 and the 0.478 moles of the nitrate. Adding them together, I have 0.717 moles, or over here, I multiplied, okay, 0.239 times the resultant 3 moles of ions that I got. Either way, I'm coming away with a molality of the resultant solution of 0.717 moles. Okay, I'm gonna go back. 0.717 moles. That's actually it's not. That's the number of moles of my resultant solution. So when I go to step 3, which like the other problems ask me to calculate the molality, I've got to divide. My number of moles is not 0.239. It's 0.717 divided by, in this case, 1 kilogram. That part of the problem is easy, right? So it's 0.717 divided by 1 kilogram of solvent. Again, in this case, it's water. So I have a molality of 0.717 molal, okay? Step 4, final step, is to figure out the change in the freezing point temperature using the freezing point temperature change equation. Again, this, because my solvent is water, it's going to be negative 1.86 degrees Celsius per molal. I multiply that by the molality I calculated in step 3, and I come away with a change in the temperature of negative 1.33 degrees Celsius, okay? So if I add a little barium nitrate to the ice on my street, it's going to lower the freezing point of that ice about a 1 1/3 degree, okay? Notice that that's a little bit more significant than the first few problems that we've done. And this is why in the winter, we throw salt down. Salt is an ionic compound made up of a metal and a nonmetal, okay, a cation and an anion, as in the case of barium nitrate, and we don't go out there with sugar, which is a non-ionic but covalent compound. Doesn't have as great an effect on the depression. And the same thing when we're making our pasta. We don't throw sugar in the in the pot we put a salt in for the same reason. Salts, being an ionic compound, are going to produce more ions in solution and therefore have a greater effect on, in this case, the boiling point elevation, causing our water to boil off at a greater temperature and causing our food to cook faster. That's it, folks. Check Sycamore for some problems for homework, and we'll see you in class.